Hello, I'm Sam, and this will be your quick start guide on how to use ElectroMag Nodes. When you install ElectroMag Nodes and you add it to your asset browser, you'll notice there are two subcategories, electrostatics and magnetostatics. There are also advanced categories. These advanced categories contain nodes that are only available in the Pro version, such as the capacitance solver and the inductance solver. If we have a look at the magnetostatics nodes, the nodes that are available to you are the arrow grid, the field lines, field planes, field point, field volume, inductance solver, that's only in the Pro version, and a toroid curve. And I'll be talking about each one of those quickly. Let's start with the arrow grid. Before starting, let's erase everything in the scene. So we have nothing in here. And let's drag and drop our grid. Now, when we drop this in, we will notice there are two objects that have been added. The first one is a geocurve, which is the coil. And this is a procedural coil defined in geometry nodes. And the second one is the actual arrows, which represent the magnetic field intensity and direction. Let's go to the viewport shading so we see what we have here, and you notice that this is the arrow grid. It's very white in the center of this coil and less brighter outside, and the arrows get smaller, and that indicates that the field is stronger in this area and less strong outside. Let's have a look at our geocurve object, and let's go to the geometry node editor. So this is essentially a spiral curve, and I've got a transform node. So I'm creating two spiral curves, and I'm offsetting it by 0.5 and joining it here. Let's to make things easier, let's remove one of them, so we only have a basic spiral curve. Now, I can change the parameters of the spiral curve. I can add more turns, I can increase its height, and I can change the radius. And you see how the field arrows, they change quickly uh, based on how this curve gets changed. Now, the arrow grid itself, if we go to the modifier panel, we'll see a set of options that we can change and configure. The first one is the target coil curve, and this is essentially telling the arrow grid which curve to calculate the magnetic field off. So we are targeting the geocurve. Now we could target any other curve you want, and I'll show you how to create your own curves for this. The second option is the units. By default, we are using Blender's units, which is in meters, and so by checking this, you change it to centimeters. The third option is the wire radius. Now, although this coil, it's only a line curve, essentially it has zero width, we can still specify a radius for that, and that'll be very important, especially when we calculate the inductance. The next option we've got is the coil resolution. So the arrow grid is sampling this curve, and so this tells it what are the number of samples to use. The higher number of samples, the more accurate it is, and the lower number of samples, it becomes less accurate. So as you can see here, as I decrease number of samples, it becomes not accurate at all. So let's keep this as 20256. Next, we've got the grid size X and Y, and this essentially defines the dimension of the grid in the X and Y direction. So if I make it smaller, I can make it smaller, and I can make it bigger. I would avoid changing the scale in the viewport, so I'd always want to keep the scale in the viewport as 1. You can change it, but just make sure that they are equal in scale. If you do have them at different scales, then the results become inaccurate at all. So let's go back to let's clear the scale. I'll test. Next, we've got the number of vertices in the X and Y, so number of arrows in the X and Y direction. So I can have less arrows, and I can have more arrows, as you can see, and it's still fast and responsive. So again, if I change number of rotations of the coil, it's still very fast and responsive. And the next option we have is the arrow scale, so I can make the arrows smaller. If I have too many arrows, they overlap, so I can change the scale. Let's go back to 20 arrows. Let's go back to a scale of 0.5 per arrow. That's maybe too much, 0.2. Okay, now let's go back to our curve, and it might be difficult to see the actual curve that we're working with. So we would want to add some thickness to it. So in other words, convert it to a mesh. Now, note that the magnetostatic solvers only operate on curves. So if I change this to a mesh, it will not work. So let's try and do that and see what happens. So if we say curve to mesh, we put it here, then the arrows disappear, and that's because we only have a mesh output. So the correct way to do it is to input the original curve and then combine the mesh with the curve. And so now in our output here, we've got a mesh output and a curve as well in the same object. So let's add some thickness to it. Let's get a curve circle, and let's 8 resolution. Let's make that 0.05 as a radius, and this is our coil. Maybe it's a bit too thick. Let's make it 0.025, and so this is our coil. Let's go back to our arrow, and let's obviously match the curve wire radius to the actual radius of the curve. At the moment, there's no way to obtain this value, so they have to make sure that the core wire radius is equal to the radius that you specify here. So it's actually 0.02. We'll have a look at, let's go back to our geocurve and let's make it smaller, easier to work with. And so if we go back to our grid and have a look at the node setup for it, it might look complicated and a bit untidy. I've tried to label the important parts of it. Now, the nodes in orange are the ones that you could configure. So let's have a look at this node here, and this is a node group B field, which actually is the most important one that calculates the field value in every point. Now remember, with this current version of ElectroMag Nodes, we assume that we're working with air core coils, so we're using a permeability of air, which has a mu r value of 1. So future version of electromagnetic nodes will have support for materials. So back to this node, and you can see here I've got a value which is current, and the reason why this value is not in the modifier panel, and that because in the actual grid where I'm using the normalized B field value. So I'm calculating the B field value everywhere, and I'm normalizing it such that the maximum value will always be 1. And so as you can see here, if I change the current in the coil, nothing changes because everything is normalized. However, if I make it -1, you'll see that then it flips. And so it means that the current is flowing in the reverse direction. Let's bring this back to 1. Next thing you can change is the clamp value. And so essentially this changes we're assuming, because we're normalized all the arrows, so they have a scale of 1. Now, in some cases, if you have a certain shaped coil, you will have very strong fields in one area and less strong fields in other areas. And so that might affect how these arrows will appear. And so you can have a clamp value here. So if we reduce the clamp value to 0.5, you'll see that, for example, these arrows here have reduced in size. So let's bring this back to 1. And that's your arrow grid. The next node that we'll have a look at is the B field plane. So let's drag and drop this in our scene. And again, this will also come with its own curve in the scene. And with this one, basically, it shows you a heat map of the electric field, so of the magnetic fields. And so it's stronger and white and brighter in the center and less bright and red outside of this further away from the coil. It also tells you what is the maximum and minimum magnetic field values, although these numbers depend on the resolution of the grid. So you need to be careful with the resolution to get accurate values for these. So in a similar way, in fact, let's delete this curve that it came with. And let's reset the position, Alt-G, back to the center. And also let's have a look at the modifier panel for this. So we're targeting a geocurve 001, which is the one that it came with. We don't want that. We want the original curve that we had in our scene. And that is, if we use the eyedropper, and that is this one here. Let's hide the arrow grid. And also let's have a look at what we have here. A similar set of parameters, coil wire radius. This value was 0.02 for our curve. And the coil resolution, which is the number of samples for the coils that we're targeting, and the plane size X and Y. Now, if we have a look at the wireframe for what we have, so to bring up the wireframe, go to here, and essentially how this works is that in each vertex, it's the magnetic field is calculated at each vertex. Obviously we could add more vertices in our scene to get more accurate values. However, if you notice that our plane is very large for this coil, so we would want to reduce it, and let's set this to 1 so that we avoid having to add too many vertices in our scene. Also, let's move it to a little bit here. So now I think it's we have a good number of vertices to capture the magnetic field. Let's turn off wireframe mode and let's see what we have. So, and you'll see that in this particular in this plot, you see that the magnetic field is actually very weak in this area here, and this is expected for a solenoid, so it does make a lot of sense. In terms of the magnetic field, these values, there's another modifier here. It's called B field legend, and you can adjust the scale of this legend and move it in direction you want. Now, as I mentioned, these values, the maximum and minimum, depend. I wouldn't say they're very accurate because you'll see that as I move this plane a little bit, they do change, and they change quite a bit. So it goes from 12 if the plane is positioned here, and maybe up to 14 in some cases. And that's, as I mentioned, because we're moving the sampling, the points in space that we're sampling it. So use these max and minimum as a rough guide to indication to what the field strength is. If you want accurate values for that, the best way to do it is to make your field plane smaller. So let's see. Let's say, for example, we're interested in this area here. Let's make our plane smaller in the X and Y directions. Let's grab it up and bring it up here, a bit more smaller than that. And now let's turn on wireframe again. And you can see we've got a large number of samples now, actually. And let's turn off grid so we can see better. We've got a large number of samples here. And let's have a look again at our maximum and minimum values, 12.59. Turn off wireframe. In fact, I can use Ardops to do that quicker. And so if I move this pin around, you see it does change quite less now. So it becomes more accurate. And I can add more vertices. Let's make it 200. And it does become slow, but now it becomes much more accurate. And so we could be certain that the field value, maximum field value, is about 13 microteslas for this coil. And that is the 2D plane. The next node we'll have a look at is the B field point. So let's grabs into our scene, and you can notice that Blender placed all the way down. Let's reset the position by pressing Alt-G. Essentially, this is a single point measurement of the magnetic field anywhere in 3D space. And you can see as I move this point around, the arrow changes direction, and also the magnetic field value as well. And I think this is the most accurate way of measuring the field at any point in space. Also, if we look at the modified parameters, we've got the same familiar set of parameters, which is the coil resolution that we're sampling, the coil wire radius. This is going to be a very important number to determine the field, especially when you go inside the wire. So with this, this wire has a radius of about is 0.02 meters. So let's go back here and update this value, 0.02 meters. Um, and also we've got other parameters. We can hide and display text and adjust the text size and location. Also adjust the arrow scale. We can also change the color of it, so we can make it brighter or less brighter. One interesting exercise to do is determine to see how accurate this calculation is. And perhaps the best way to do it is to compare it to a theoretical value. So let's compare this to the theoretical value of a straight wire. So let's heighten our curve. Let's create a straight wire by going to curve Bezier. Let's straighten it, rotate it by 90 degrees, and let's give it some thickness. So let's create a new modifier. I already have one created for this called Winding Viewer. Essentially, this is creating a wire and giving it a thickness of 0.1 meters. Let's go back to our cursor, B-field point, and let's make sure we're targeting the actual wire, like the eyedropper, and let's bring our cursor all the way here. Let's make sure that our radius is set correctly. This should be 0.1. So let's go back here and say 0.1. Now we know from theory that the magnetic field strength at exactly on the surface for this coil should be 2 micro teslas. For a wire with 0.1 meter radius, it should be 2 micro teslas. Let's make sure our arrow is placed at the surface, so it's going to be 0.1, and you can see it's 1.99 compared to a theoretical value of 2. Another thing to note is, well, the magnetic field does decay as you move away from the coil. It gets smaller and smaller, and it also decays as you go inside the coil. So let's see what happens. Let's go inside the coil, and notice that as you go inside, the magnetic field starts to shrink and shrink and becomes essentially zero, exactly at the center. And then it goes back, becomes stronger as you leave the coil. Um, and we could go back to our grid, and we could visualize the magnetic field. So let's select the arrow, and you can see that as you would expect from the right-hand rule, that for the current flowing in the y direction would give you this magnetic field that would rotate around. And this is the B field point. The next node we have is the B field line, and this is one of the nodes that I really enjoy working with, and it's a lot of fun to use. So let's reset position, and essentially how this works is you grab your field line and you place it in a position of interest. And then how it works is that it calculates its direction as it moves along the line. So for this type of coil, the field lines, we expect them to be to rotate in this direction. And as if we duplicate this line and we bring it closer to as a center, we will see that it becomes straight as you would expect. If you look at the modifier panel, we do have only one parameter to work with, which is the field line length. And I make this shorter or longer. Note that if I make this too long, it becomes inaccurate. So you'd want to keep this around, say, 0.1 or 0.2. And then if I bring this all the way here, you'll see that is, as you would expect, it will start to form a closed loop, and the feed lines get more sort of closer to each other, more dense. And this is how it looks like in 3D. If we sort of change our curve to just a regular circle, so let's set number of rotations to 1, height equal to 0, and you can see now, as you would expect, that it forms a full closed loop. This is a very fun node to work with, and it's really can make some interesting animations with it as you change your coil dimensions. Have a look at my twisted pair demo coil, which is very entertaining to watch. The last node we have is the B field volume node. Let's add this to our scene, and this creates a 3D grid, 3D volume grid of arrows. It's useful to view magnetic fields for coils such as toroids. If we have a look at the modifier panel for it, again, a very familiar set of parameters: our target coil curve, units, coil wire radius, and resolution. and the volume size dimensions, and the volume resolution, which is essentially the voxel size. So if I make this larger, I can have bigger voxels. Essentially, I have less resolution. If you do want to make this a low number, you got the volume density, which is number of arrows. So if I reduce this, I get less arrows, and the arrow scale and the point seed, which randomizes the location of these arrows. If we do have a look at the toroid curve that it comes with, let's go to a geometry node editor. Essentially, this starts as a spiral, and then it gets deformed over an arc, and I can change my arc radius, so I can make my toroid bigger, like so. I can increase the height so that it gets closer to its start and end points. I can change the number of turns, so I have less number of turns in my toroid, and I can make it larger radius. And you can see how the magnetic field the magnetic field arrows change accordingly. And this is the B field volume. As I mentioned previously, the magnetic fields are displayed are the normalized values. If you'd like to see the absolute values, the best way to do it is to go to the Spreadsheet Viewer. And so you can see here that for the arrow grid, data available to you is the B field magnitude, the normalized value, and the direction of the magnetic field at each point. It is at the moment you're unable to export this data, and it's difficult to tell where these numbers actually are. Best way to do that is to use the 2D plane viewer or the single point viewer for that. In a future update, you have the capability to export these numbers. You can control the way the fields are displayed by changing the shader setting. So if I have the 2D field plane, if I go to the shader editor, and this is the current node setup that I have. So I'm taking in the B field normalized value, and that's because I know my values will range from 0 to 1. It will make things much easier going forward. That then goes into a color ramp, into a map range node, which then connects to a black body. And this is what sets the temperature and the colors. The black body ranges from 500 to 5000. You can use this color ramp to make changes if you want. I've also got an emission value as well. I can adjust the scale of the emission, and I've got a color ramp, and that also connects to the alpha value, so I can make my weakest field values disappear. I can only focus on the brightest spots, for example. If you want, you can change the colors and not use the black body at all. You can have your own color arrangement. So I've got this, for example. I can connect it here, and I will have these colors now. You can also use the absolute values of the field values, but I would not recommend you use that, because then you'll have to change this entire setup, as your values will no longer range from 0 to 1.